So I want to highlight just a few differences between the reactions that take place under acidic and basic conditions. There are three types of conditions we can see for our reactions. Neutral conditions, like what we see for acid chlorides and anhydrides, acidic conditions, and basic conditions, like what we see for esters and amides. The first thing to highlight is that under acidic conditions, the vast majority of the charges we form are going to be positive charges. Under basic conditions, most of the charges we form are going to be negative charges. Under basic conditions, the negative charges that we form are going to be much more stable than anything that would be positive because we have an excess of base under these conditions. The opposite is true for acidic conditions. In acidic conditions, the charges that we form that are most stable are going to be positive charges because we have a surplus of protons and we don't have great bases in our reactions. So under acidic conditions, what we form most often is positive charges. Under basic conditions, what we form most often is negative charges. We really don't form the opposite charges under those conditions, meaning in acidic reactions, we don't form negative charges, and under basic conditions, we don't form positive charges. The conditions for an acidic reaction include things like H3O+, HCl, H2SO4, whereas the conditions for a basic reaction include things like sodium hydroxide, sodium methoxide. There's an important difference in the mechanistic steps for our acidic and our basic reactions, so that if we look at a generic example like this one where we just have X as our potential leaving group on the carboxylic acid or the carboxylic acid derivative, we could look at the resonance first, and in all of our carbonyl structures, that resonance shows the separation of the charge at the carbonyl. The oxygen has a negative charge and the carbon has a positive charge. That tells us that under acidic conditions with lots of protons floating around, that negative charge is going to be what we fix first. That means that it's going to be able to pick up a proton from the H3O+, the H2SO4, the HCl, one of the acids in our solution. Whereas under basic conditions, when we separate those charges at the carbonyl, we have the negative on the oxygen and the positive on the carbon. In this case, there's no protons for this oxygen to pick up. We've got a lot of bases around, so the O- is a pretty stable charge under these basic conditions. That positive charge, however, is going to be much more reactive. That's going to be what we fix first because we have lots of strong nucleophiles in this reaction to donate electrons towards that positive charge. One of the other key differences to note is how the tetrahedral intermediate is going to collapse under acidic and basic conditions. Under acidic conditions, we're going to kick out neutral molecules like methanol or water, or amines under the conditions of our reaction, whereas under basic conditions we can kick out strong nucleophiles like methoxide and hydroxide, so that if we look at a tetrahedral intermediate like this one that collapses, it's going to collapse where both of these oxygens are in a neutral state, where this molecule of methanol has been protonated, so that as it collapses we get the neutral carboxylic acid and the neutral molecule of methanol. Under the basic conditions, we have a tetrahedral intermediate that looks like this, where we have that O- charge in our tetrahedral intermediate, and as it collapses back, it's going to push out the methoxide ion in this case and leave us with the carboxylic acid, which we know immediately leads us to an acid-base reaction in our saponification reaction.